You can put either one on top, you know that. You can arrange it either way. If you put the heavier element on the top over on the rate column and the lighter one on the bottom, you get a number that's a little bit easier to work with. This is one of those kind of problems where you can get the right number and still get the wrong answer. Chlorine effuses at 6.28 times the rate of nitrogen. So what this means in real terms, the first thing you should do when you get the number is look at them and say, which one of these is going to move faster? Well, you know it's going to be the lighter or the heavier. The lighter element is going to move faster. So if you have this small number, something less than 1, the gas is moving at a slower rate than the other one. Let's go back to this slide. When we get that number, 0.628, this is a ratio and it has an invisible 1 under it. And that's where that meter stick comes in. For every 1 meter that nitrogen moves, chlorine's only going to move 0.628 meters. Here's our basic sentence structure. You've got your rate of something over your rate of something else, and you get some number. And in this case, we got our 0.62865, and that goes on and on and on. The first blank in your sentence is going to be whatever your top chemical was for rate. So here we're going to say Cl2 effuses at. The next blank is going to be the number that you got. So 0.62, and we can round now, say 0.629 times the rate of, and then the thing that's going to go in the next blank is whatever was on the bottom of N2. In other words, if you need another way to think of it, for every 1 meter that, again, that thing that was in your first space, Cl2 travels, the thing that was on the bottom, nitrogen, will travel, and then you're going to have that number again, 0.629 meters. Does that make it clearer? Yeah. So what if you had set this up like this instead of the way we had it in the last example? You're going to get a different number, right? So how can you get 2 numbers for the same problem and still get the right answer either direction? Let's show. All right, so we're going to get a number done this direction. So we used the same 2 gases and we got a different number. But we still have the right answer. Because if we remember that there's an invisible 1 under here, now we're saying nitrogen effuses at 1.5907, etc., the rate of chlorine. We're back to our sentence, and we're starting off with whatever's in that top blank. Nitrogen effuses at, we'll say 1.59 times the rate of chlorine. Would you expect that nitrogen would effuse faster than chlorine? Yeah, because it is lighter. It's got a lower mass number. In the time that chlorine could travel 1 meter, nitrogen could travel 1.59 meters. Problem that you can have where we're asking you, you've got one known gas and you're told that there's another gas that effuses at some multiplier of its rate. What's its approximate molar mass? So here we're told that there is some gas that effuses at 3.5 times the rate of, that is C6Cl. That's chlorobenzene. It's 6 carbons in a chlorine atom. What is its approximate molar mass? The first thing we want to do is rearrange because we are going to solve for one of these. It's really easy if we pick the one on the top. So we've listed our variables. We have the mass of the chlorobenzene. We're looking for the mass of our unknown. The rate of the unknown gas, it effuses at 3.5 times the rate of the chlorobenzene. So we're going to write it exactly like that. Say this first. There are 2 ways to solve this for the next step. You can move stuff across the equal sign first, or you can square things first. Either way, doesn't matter algebraically. Okay, so right now we're down to just needing to square everything to get it solved. Does that make sense algebraically? You all good with that? Okay, so now we're down to something that's solved for gx. We just need to do a substitution with the rate. And if you remember from the last slide, the rate of gx is equal to 3.5 times the rate of the C6Cl. So we're going to substitute that in. Alright, so now we're at a point where we're going to do a little bit of magic, and that rate cancels out. Now in this case up here, everything goes away. But in this case, that 3.5 remains, and that's important. Okay, so we're down to having numbers, and what's our final answer? Okay, so we know that the mass of our unknown gas is somewhere in the neighborhood of 8.77 grams per mole, and this is a rough value. So it could be 9 times, it could be 9 grams per mole, it could, on the order of magnitude, it could be somewhere around 8. This is a rough value. This is not a real precise number, so you're not going to get a great match, but it's going to point you in the right direction. Okay, so we're going to do a quick special segment, special algebra refresher on solving for one of these masses. Now, here's the nice thing. Since you're setting up this problem and you're deciding which gas you're going to call A and B, you can always make sure that whichever one Gesundheit you're solving for is the one that's not in the denominator. Okay? You should never ever have to solve for the one that's in the denominator on these, because if you did, it's your own darn fault. You put it there. So just make sure that you're setting it up so that you're solving for the one on top. You can solve for either of them, but it's a little bit, it tends to throw more people for a loop. More people make mistakes when they're solving for the thing in the denominator. Okay, the key to remembering everything wonderful about algebra is, if you do it to both sides of the equation, it's legal. First thing we want to do is isolate this on its own side of the equation. So I'm going to multiply both sides by the square root of the mass of B. That will give me this. So those cancel out, and now I have the square root of the mass of A isolated on its own side. Okay, so now we've got the square root of the mass of A isolated, but we have to get it out from under the radical. Remember, algebra, as long as you do the same thing to both sides, you can pretty much do anything you want. Paint it purple, call it Fred, doesn't matter if you do it to both sides. So we're going to square everything. We're going to square both sides. If we square the square root of the mass of A, we get the mass of A. It's magic. If we square the other side, we get the rate of B squared times the mass of B times the rate of, divided by the rate of A squared. So now we've got something that we can work with, and typically in these kind of problems we're doing a substitution for one of those rates and something will cancel out. Alright, so now back to the gas problems. Here's the clue I'm going to give you. Do you remember that we substituted in the rate of effusion as a proxy for velocity? You're just going back to velocity. So velocity of B over velocity of A. And in this case, again, you're assigning the A and B, you're just picking one to solve for. So these are pretty easy. If you want to see a problem like this, look at number 3 on page 355, and the answer is in the book for you, so you can see if you're doing it wrong. But these are fairly simple, and those are the 3 kinds of problems that will be on your quiz tomorrow.